Hello everyone, let us continue with our video lecture today, and today it will be on the hands-on individual activity 2-3A on the topic of force convection. So this is the question which you have seen last week. The question is about the internal flow of the air which is flowing through the tube having the inside diameter of 38.1 millimeter. The velocity is 6.71 meter per second, and the average temperature is 349.9 Kelvin. The pressure is kept constant at 1 atm, and the inside wall temperature is also held constant at 477.6 Kelvin by the steam condensing outside of this tube wall. Calculate the heat transfer rate in this system. And now what we are going to do is we are going to do this in a step-by-step guided exercise table. So we'll go to that table. Okay, now we are in the table that I have prepared for you. You can use the same table and complete the table. So from here, you will see that the first step is always to draw the illustration and to completely label this illustration. Okay, so from this question, we have given all the information which I have already labeled here. And just to give you the definition, because we are given with the average temperature of 349.9 Kelvin, so the average temperature here is actually the temperature between the inlet bulk temperature, which is TBI, and also the outlet bulk temperature, which is TBOut. So in this case, of course, the inlet and outlet temperature of the bulk air is not given, but the average temperature is already given as 349.9 Kelvin. So no need to worry, because actually this is the temperature that you are going to be needed for your calculation. Okay, now, so we have the average temperature of bulk, and also we can define the area, which is the surface area. So that's why I have the subscript S here, which is equals to pi dl for the cylinder, since the tube is having the cylindrical geometry. Okay, so what is next? Next is we need to assume, or we need to state the basis. Here, what we can do is we can assume that the tube is very long, which is the ratio between length and diameter should be bigger than 60. Why this is the case? This is because we want to simplify the calculation. Okay, so if we do this assumption, which is long tube, then we don't need to do the correction for convective heat transfer. If, let's say, our problem here is turbulent and the L is less than the ratio of less than 60. Okay, so that's why in order to simplify the calculation, we can assume that the length over diameter ratio is higher than 60, as we don't need to do the correction for H. Okay, so if you don't state this, then your calculation is not fully completed. So please recall this slide which I have mentioned last time in the lecture. So here is very important. Okay, so that's why it is important to assume that the length over diameter ratio is bigger than 60, because then we can just use this equation without the correction. Okay, so if you don't state that, then you might need to do the correction, and it just add the additional step, and it just make the calculation more complicated, as well as you might have the some mistake during that step. Okay, so that's why we want to avoid that error by taking the assumption of L over D is bigger than 60. Okay, so if you still remember, this is only the correction is only needed if your Reynolds number is in the turbulent flow region. If your Reynolds number is in the laminar flow regime, okay, which is less than 2100, then you can use the Nusselt number without any correction needed for the H value. Okay, so that means these are the conditions or requirement that I have asked you to fill in the table, which is table for activity 2-2, and I hope that you have completed the table by now. Now, if you still remember, we are just completed the step 1 and step 2. So for step 2, the length here is not given for the tube, so we can take the basis of 1 meter length. It is easy to take 1 meter because then you can just multiply your answer with any value of L, which is the final step. All right, so just take 1 as the basis at first, and then we will go to step number 3, which is to determine the physical properties. Okay, here, since the fluid is air, so it is important that you take the air as the fluid. Okay, so you need to calculate the physical properties of air. Okay, so if in the question you are given with water, so then you have to determine the fluid properties of water and at which temperature. So since this is internal flow, so you have to take the physical properties at the TB average, which is the bulk temperature, the average bulk temperature. So you have to do that, right? So the TB average here is given as 349.9 Kelvin. So you need to calculate or determine the physical properties of air at 349.9 Kelvin. So what are the properties that you need? So these are the properties that you need, which is heat capacity, the viscosity, the density, the thermal conductivity, as well as Prandtl number. Okay, so this is the first one which I have shown. So here the physical properties that you need is at 349.9. So you should look these properties from the table. So what are the table required? So I will just show you in a short while. Okay, so for air, you can refer to appendix 8.3-3 from your textbook, okay, which I have shown it here, because some of the textbook, if you have new textbook, you don't have appendix, but if you have edition 4 of the textbook, then you are going to find this appendix at the back side of the book. Okay, now the TB average is 349, which is between this and this temperature. Okay, between this and this temperature, right? Okay, so 349.9 is between this and this temperature. So I'm going to show you, of course, in the first place, on how to interpolate the data. So I want to show on the viscosity. So here is mu times 10 to the power of minus 5. So you have at 338.8 is 2.03, and at 366.5 is 2.15. So what you need to do is you take this value and put this into our guided example. Okay, so this is how you interpolate But here, what you need to take into consideration, because the value of the viscosity just now is 5, right? But for the calculation, you have to take minus 5. Okay, so this is the common mistake which done by the student in the previous time, but I hope that you don't do the same mistake. So the correct one, it should be negative 5 here when you calculate. Okay, even though from the table is with power of 5. Okay, so here for the sake of calculation, you should take minus 5. So this should be the viscosity at 338.8, and at 366.5 just now is 2.15. Okay, now since this is the viscosity calculated at the bulk temperature, so I have mu B as the subscript. Okay, so you will see that mu B is only needed for internal flow. For external flow, we only have mu without any subscript. Okay, then from this calculation, you can just press your calculator to obtain the mu B. So mu B here in this case will be 2.078 times 10 to the power of minus 5. And please do not forget to write down the unit. Okay, I want you to write down the unit, because later on when you want to calculate the Reynolds number and Nusselt number, please make sure that the unit is unitless for Reynolds number and Nusselt number. Okay, so now, so if you have already obtained the value for viscosity mu B, which is viscosity at the TB, then you can obtain the viscosity mu W at TW. Okay, for TW, since the TW here is 477.6, okay, please look up the value of mu W at TW. So the mu W should be also mu of the air at TW, which is 477.6. So please look it up at the table. So at 477.6, so since the temperature is the temperature same as in the table, so you can straight away take the value of mu W. If the temperature is not at the given temperature in the table, then of course you need to do the interpolation, which is the same step that I have just shown just now. Okay, so for the rest of the properties, which is density, heat capacity, okay, so heat capacity here is in kilojoule per kilogram Kelvin. So if you want to calculate for Reynolds number, of course you should times 1000. Okay, so it should be here instead of 1.009, you should take 1009, okay, for joule per kilogram Kelvin. And then you should interpolate. So for CP, you don't need to interpolate, right? Because the value is the same. For density, you need to interpolate because the value is different. The value of thermal conductivity, so you should also need to interpolate the value, and also the value for Prandtl number. Okay, so the other two value is not of interest in for your calculation. Okay, so this is the physical properties of air. Okay, so just to give you an overview, let's say the question is on water. Okay, water as the fluid, so you should use table 8.2-11 instead. Okay, but in this case, of course, for air here, you need to consider this, because here when you calculate, it should also be 10 to the power of minus 3. All right, but of course this is not the case for our question, so let's do not confuse ourselves. So you should focus on table A.3-3, in order to get the physical properties of air at 1 atm. Okay. Alright, so I hope you can already complete the interpolation to get the value for rho, Cp, K, and also Prandtl number. If you have done that, let's go back to our table. Okay, so here you need to complete your calculation to get the value for Cp, to get the value for mu, rho, K, and also Prandtl number. Okay, so please be noted, please be reminded that you should show the interpolation at least for one of the property. Okay, at least one of the properties you should show the interpolation. The rest you can just write down your answer for Cp, rho, K, and also Prandtl number. Alright. Otherwise you will not get the complete mark if you don't show at least one of the interpolation. Right, so we have completed step 3. We are now in step 4. So for step 4, we need to calculate the Reynolds number from this equation. So Reynolds number is rho Vd over mu. Then from there, you can distinguish whether the region is laminar, transition, or turbulent. Okay, so from my calculation, I have obtained that the value of Reynolds number is higher than 6,000. Okay, so when it is higher than 6,000, then the answer should be in the turbulent region. Okay, since the answer is the Reynolds number is bigger than 6,000, and when the Reynolds number is bigger than 6,000, so you should use this equation. Okay, so if you want to double check, so let's go into our activity 2-2. So here, turbulent, okay, Reynolds number is larger than 6,000. So this is the Nusselt number equation. And since we are at the fully developed region, which is L over D is higher than 60, so this is the equation that is required to calculate the Reynolds number, which is Nusselt number equals to 0.027 times Reynolds number to the power of 0.8 times Prandtl number power of third times viscosity in bulk divided by viscosity at the wall power of 0.14. Import this into our guided exercise. Okay, so after you have imported this, okay, please calculate the Nusselt number, and then please calculate the H, which is the convective heat transfer coefficient. So Nusselt number here, you should obtain you should be able to cancel out the unit. Okay, and to obtain the dimensionless unit for Nusselt number, and for H value in step number 6, when you already get your Nusselt number, then you can calculate the H. Okay, you can calculate the H here. So just rearrange this equation, and of course here, since we have the cylinder, note that all the Reynolds number, Nusselt number is going to be calculated with the subscript D, because we will consider dimension D. Okay, so rho Vd over mu instead of rho Vl over mu, because we are going to consider the dimension D. Okay, so that's why for Nusselt number we also have subscript D. Okay, so just rearrange this equation. So you will get the H is equals to Nusselt number times the K divided by the D. Okay, and you will get your answer, and that's why you don't need to further continue to correct your H because you have already assumed in the first place that L over D is larger than 60. Then you can straight away take this H value, okay, plug in this equation in order to calculate the Q. Okay, so here in order to calculate the Q, you need the surface area, which is pi dl, okay, and then the H value, which is obtained in step 6, and the difference in temperature. So the difference in temperature, because we are considering the temperature difference between the T-wall and also the TB average, which is the average temperature inside this tube. So from there you can obtain your Q, and my answer is 527.3 watt. So I hope that you can complete this guided exercise 2.3a and post your answer in e-learning. If you obtain same answer like mine, so that means you are on the right track. Okay, good luck about that, and post your answer in the e-learning. So I will continue in the next video with the next guided exercise and next activity. Thank you.